Hello. Sound check. 1, 2, 1, 2. Sound check.
Nice.
Here, I can try. Sound check. Hello?
What are you doing?
No? Do you want to check the sound or no?
No, it should work.
Oh, okay.
Yeah, I think that you can hear.
I thought you wanted me to check the sound.
No, sorry. So this is the... Está un poquito... Hello. Thanks everyone for coming to one more seminar. Today I'm very happy to have Alex presenting his thesis work with the Lombards in interprogramming. So thanks Alex for coming.
Gracias, Diego, por la invitación. Yo soy un investigador postdoctorato a Montréal, in Canada. However, I have to switch to English now, so that's it. That's all I know. I'm very happy to be here. I've loved being in Chile. I've been here for a week, and I'm just amazed by this country. And also, it's a very unique country for my field, for industrial engineering, operations management, because so the United States and North America, they kind of have a stronghold on some researchers. They have, I think that there's somehow a lot of people go there for education, for PhD, etc., and then they stay there. But in contrast, Chile has this kind of unique reputation that first of all, there's a lot of industrial engineers and people working in operations management. But second of all, many of the great researchers come here back to Chile to do their work. And that's different from, let's say, maybe Turkey or other countries that have also really great contingents of industrial engineers, but a lot of them happen to stay in North America. And so that's something that, I experienced yesterday. We had this day of discrete optimization, and just it's, hey, invite some people, 35 people come, and 5 speakers, local speakers. Actually, there were 6, 1 wasn't able to make it. And it is really quite amazing. So anyway, Diego, thank you for the invitation, for hosting me, and for this country. It's not all thanks to you, but the country, I mean. So I'm going to talk a little bit, as Diego said, about part of my dissertation research, which is with Egan Ballas, who is the father of disjunctive programming. And he passed away in March, but I'm still continuing a lot of the work that I did with him, and we kind of had a lot of open ends. So at the very end of the talk, I'm going to also kind of point out a few ongoing things with Egan that I'm still working on to complete. And the topic is something we call V-polyhedral disjunctive cuts. It's a new cutting plane technique for general integer, mixed integer linear programming. And the idea is, can we do something more efficiently? Can we generate these cuts more efficiently than were done previously than other competing techniques? And ultimately, the goal is to try to see if our techniques, our methods, can be incorporated into modern integer programming solvers like Gurobi and Cplex to try to improve the internals of them. And there are challenges along the way, and I'll point them out. these are not implemented in Gurobi. Nothing like this is implemented in Gurobi. Only very simple things are implemented in Gurobi and Cplex. And I will kind of point out why, and there are very reasonable things that prevent them from doing this, and also kind of what we're working on to try to move on from that. So just to start off a little slowly, what is the setting? The setting is mixed integer linear programming. We'd like to optimize something. We'd like to maximize something good. This applies almost anywhere. You want to maximize something good. But you have constraints. You have some kind of restrictions on where this good thing can be. And in particular, these constraints that we're going to look at in this talk are linear constraints. But this is not too much of a restriction in the sense that many applications are sufficiently described with linear applications, or at least you can make a lot of progress with just linear constraints. However, we don't just have linear constraints, we also have integer constraints on the variables. And what that means is that within this region, the yellow region P, which was the set of constraints, we actually want a set of points from there that is actually the set of feasible points that we're looking at. And those points are actually kind of hard to find and to optimize over. So here is this region Pi, which is the set of points. And we're going to also work with the object, the convex hull of Pi, which is the convex hull of those sets of points. And you can't efficiently optimize over Pi or the convex hull of Pi because you don't have access to that. You only have access to P. And what do? You optimize over P, because that's what you have access to. And you get some kind of solution, which throughout the talk it'll be x bar. And that solution is not going to be in Pi. It's not going to be an integer solution. It's not going to be feasible to our integer constraints. It'll only satisfy those other linear constraints. And we're going to tighten P with extra linear constraints. Okay, so a little bit more formally, we're going to work with that object P, which is defined by a set of linear constraints ax greater than or equal to b. And Pi is, again, ax greater than or equal to b plus those integer constraints on some or all of the variables. And LP is going to denote the optimal, not the optimal solution, it's the optimization problem over just P. And IP will be the optimization problem over Pi. And so we're going to start with x bar. And specifically, the cuts that we're going to look at are general purpose cuts. Actually, historically, in the 80s and before, cuts were always special purpose, or the ones that were used in practice, meaning that they use some kind of problem structure. For example, for the traveling salesman problem, there would be something specific from that problem structure that you would be able to use and then apply. But if you got a general integer program, it wasn't so common to apply cuts, because they didn't converge very well or other reasons. And so, but we are going to work with general purpose cuts. There was a revolution essentially in the 90s in which these kinds of general purpose cuts were discovered to work well in practice, and in fact incredibly well in practice, and they're critically important for solvers. The reason is that they learned that you can use them in rounds. Rather than generate one cut at a time and re-optimize, you can actually generate a bunch of cuts all together and then add them and re-optimize. And this little trick turned out to be crucial in making improvements in the solvers. And if you look at how solvers improved over the years, in the 90s, there's suddenly this big burst. And that's when Gomery cuts were applied successfully. And my advisor's work contributed a lot to that. So how do we generate general purpose cuts? The way we generate general purpose cuts is from something called a disjunction. A disjunction is this object over here. It's described by a set of inequalities, a set of probably disjoint sets of inequalities that partition the feasible region, and you want to say that the optimal solution exists in one of those parts of the feasible region. So for example, this is a disjunction. This is called a split disjunction. You take some variable xk, and here, for example, x bar k might be equal to 0.3. So a split disjunction says you want to have xk less than or equal to the floor of 0.3 or xk should be greater than or equal to the ceiling of 0.3. And any feasible integer solution will lie in one of these two regions. And so that's the disjunction. And this is basically the simplest type of disjunction, the split disjunction. But it's also the one that's most commonly used in practice. We're going to look at each of these things from the disjunction and call that a disjunctive term. So each of those individual components of it is a disjunctive term. And those are important because we can look at them separately. And the union of those disjunctive terms makes the disjunction too. And actually, when we define the disjunctive term, we actually include the original constraints also in my definition of a disjunctive term of the original constraints of P. Because you can also call the disjunctive term just these constraints without AX greater than or equal to B. And then you generate a cut, which is a cut that's valid for the union of those disjunctive terms. And it is a cut if it's valid for the union of the disjunctive terms, but not actually for P, meaning it removes actually some part of P. It's not trivial. And we call the convex hull, the closed convex hull of the union of these disjunctive terms, we call that the disjunctive hull. And we'd like to kind of get a good description of that disjunctive hull via cuts. So as I mentioned, the state of the art is that cuts are super important. We know that. That's one of the 1, 2, or 3 most important components of solver, depending on how you measure it. But they mostly come from these split disjunctions. Not necessarily exactly the ones that I showed there. It could come from slightly more complicated split disjunctions, like aggregating equations and generating things, but they end up all being able to be defined in terms of some kind of split disjunction. Moreover, if you look at a solver and you see what it does in the very beginning, it's going to generate cuts, like I said, in a round. Then it's going to re-optimize. And then it's going to generate another round of cuts. And then it's going to stop, find the solution again, re-optimize. So it's going to apply this process recursively, many times. You might see this 15, 20 times at the root node at the beginning of an IP solution process. And what is the problem with that? The problem with that is that as you continue with that process, the cuts start getting more and more parallel to each other. Because it becomes a little bit more difficult to maybe cut off the last solution. And so all the cuts start looking like each other. And that, in turn, causes the numerical issues to arise in the solver. Because the bases start getting numerically unstable. The condition number starts getting bad. This parallelism also creates degeneracy problems, which are related. And so you want to maybe also avoid that recursion as well. And so those 2 things maybe are the things that we're going to try to improve on. We'd like to generate strong cuts compared to maybe the simple ones that we currently see are implemented in practice. And we'd like to generate it non-recursively, meaning without doing really rounds, we'd like to just use the information from AX greater than or equal to B and maybe something else, but not really just adding cuts on top of other cuts. Okay, and of course we want to do this efficiently because you can generate strong cuts with a very expensive process, but it's not going to pay off in a solver. Okay, so here is again that split disjunction. It can also be convenient to look at the complement of that, which we might call a split set. It's equivalent, it's just Rn set minus that, maybe closure depending on how you look at it. And here's maybe a more complicated disjunction, or the complement of one, in which you actually have 4 terms of the disjunction. 1, 2, 3, 4. But this is, I'm showing this as a cross set. And you can see that this leads to stronger cuts. So more complicated disjunctions can lead to stronger cuts. And that's where we're going to try to get the stronger cuts from, rather than using recursion. And of course, this is not a new idea. Stronger cuts in general have been looked at in the literature for decades. I would say that you can break it up into 2 types of literature. on simple disjunctive cuts and non-simple disjunctive cuts. So a simple disjunctive cuts look something like this. It's when the set, this green set that you're cutting away, it's convex. A non-simple disjunctive cut is when this set is non-convex. And non-simple disjunctive cuts lead to even stronger cuts than you can get from any simple disjunctive cuts, and they generalize them. So you can always get a cut using a simple disjunctive cut, but you might need to use very many simple sets to generate all the strong cuts. A set like this, on the other hand, can get you many strong cuts at once. So I won't really go into the literature here, but I will point out that none of these things still are implemented in practice, and neither is mine, of course. And I want to kind of say a little bit about why. So what is the issue with stronger cuts? It's that the efficiency part. Finding them efficiently is hard. Gomery cuts, which are the baseline that we're going to use in this talk, and I actually assume some familiarity with that, they're very easy to generate. They're actually a formula that you apply to a basis. So it's very easy. Here, we're going to have to do some more work. In addition, actually, the number of things that you can choose to work with, these simple or non-simple disjunctive cuts, disjunctions rather, there are a lot of them. So for Gomery cuts, you just look at a variable and you say, oh, this variable is fractional. I'm going to generate a Gomery cut from that. And your number of choices is just the number of fractional variables that you have. But if you start looking at pairs of variables, so to generate that cross that I have, you have to use a pair of variables. So if you look at pairs of variables, now you have quadratically many options. And quadratically many is already too many in practice. Actually, more than that, for each one of those quadratically many non-simple disjunctions, the number of cuts that you can generate grows unmanageably large. So before, for each xk that is fractional, you generate one Gomery cut. But actually, you can generate lots and lots of cuts from even just xk being fractional. But now if you look at something more complicated, you get even more possible cuts that you can generate. And so that's another problem that you have to deal with. And so all of this is expensive, and what's worse is at the end of the day, you might even get an efficient procedure for generating cuts, and they might be strong. Everything looks great, but that's not your goal. Your goal isn't to get a tight relaxation of your convex hull of PI. Your goal is actually to embed this somehow in a branch and cut solver. And once you start branching, those strong cuts actually can lead to issues, which I won't talk about right now, but I just want to say that this is not even the goal. This is just a proxy that we have. So all of this is the challenge that we have in order to implement these kinds of cuts in practice in the future. And we're going to make some progress on some of these things today. So what are the contributions? We do develop a strong non-recursive cutting plane method. The way we do this is we use multi-term general disjunctions, and we embed it with branch and cut and test how well they work via computational experiments and complementary theoretical results. And at the very end of the talk, like I said, I will talk about some ongoing work on strengthening these cuts and making them yet again stronger, essentially for free. So before I go into my contributions, I'm going to talk about another baseline that is a way of generating disjunctive cuts from the literature in the 90s, but actually it exists from the 70s too. It was just rebranded slightly. It starts from a pretty simple observation. So if alpha x greater than or equal to beta is a cut, and we want it to be valid for the disjunctive hull, well, it's valid for the disjunctive hull if and only if it's valid for each of the disjunctive terms. And that's what that math says. And what we know is that if a cut is valid for a disjunctive term, we can actually get a Farkas certificate of that. And the Farkas certificate looks something like this, that your cut alpha and beta can be written as a conic combination of your terms of the disjunction. And you put that together into an LP, and you get something called the cut-generating linear program. And you need to add a normalization constraint here, because without that, this is a cone, and it's unbounded, and it's hard to actually get meaningful solutions from that as a result of how LP solvers work. But this is an LP. An LP that will get you variables alpha, beta, and VT here for each disjunctive term, that will get you a cut and the certificate of the cut together. And this is what was done in the literature and is still done in the literature for generating disjunctive cuts typically. We take a different approach, which we call the V polyhedral perspective. And I'll explain why. So again, back to that simple relationship. Here's the lift and project cuts approach. And a different way to look at it is, okay, so alpha x greater than or equal to beta is valid for PT. Well, it's valid for that disjunctive term if and only if it's satisfied by all of the extreme points and extreme rays of PT. Because every polyhedron has two representations. A polyhedron can be represented by inequalities, and a polyhedron can be represented by its extreme points and extreme rays. Just the same thing. A convex hull of those things and the inequalities that are satisfied are the same. And that's what's called the V polyhedral description when it's the points and the rays, compared to the H polyhedral description for the inequality description. The H here stands for hyperplanes, and the V stands for vertices. And this is not my notation. This is a notation from the literature. So you can take a different LP that says that alpha, beta are valid if alpha transpose P is greater than or equal to beta for all vertices, meaning all points are satisfied, and alpha transpose R is greater than or equal to 0 for all rays of that polyhedron for each of the terms. You put that into an LP, and we're going to call that the point ray linear program, the PRLP, compared to the CGLP from before. Are there any questions so far? Okay. And so what is, that sounds all well and good, but what is the challenge? Well, the challenge here is that the number of points and rays, given a H polyhedral description, given the inequalities that we have, which is how we're given the problem, the number of points and rays might be exponentially many in the number of inequalities. And so people have actually tried this technique before, and what they do is they take that LP, alpha transpose P greater than or equal to beta, and they start with just a few of them, points and arrays, and they generate a cut, and then they see, is that cut valid? Meaning, are there any points or arrays that are not satisfied? And if there are some that are not satisfied, they add them into the LP and they resolve in an iterative process, which is called row generation. However, that is expensive. Instead, what we're going to do is we're going to find a set of points and rays that immediately gets us valid cuts, with the trade-off that maybe we don't generate all possible cuts. So what are the steps that we need in order to work with this LP? We're going to have to first choose a disjunction. Then we're going to obtain points and rays. And then we're going to solve this LP for different objectives, because each objective is going to get us one cut. And so this is going to be an outline of this part of the talk. First, I'm going to say which disjunction we're going to use. So like I said before, most existing disjunctions are very simple and shallow. And what I mean by shallow is that they're somehow close to x bar. They might use maybe one of the fractional variables, or maybe two. And it's computationally expensive to work with maybe just shallow disjunctions. Oh, and what else they will do is they will use not just one disjunction, they will use many, of course, because each disjunction by itself is weak, but the set of disjunctions together is strong. So if you look at all fractional variables and you generate cuts from all of them, it's better than just looking one fractional variable and generating cuts from that. What we're going to do instead is to combat that n squared thing that I said when you have pairs of variables, we're actually going to look more than just pairs of variables. We're going to look at all of the variables and see what we can do with them. Of course, that's impractical. So we're going to actually try to generate one disjunction from those variables that is strong and is able to somehow beat all of those other shallow disjunctions at the same time. And we're going to do that by generating a branch and bound tree. Of course, we're not going to solve the problem completely with branch and bound. We're going to stop it at some point. But actually, the leaf nodes of a branch and bound tree form a disjunction. Because what the leaf nodes of a branch and bound tree, so a branch and bound is a search process. As you go through this tree, each node of the tree is saying the solution might lie in this part of the search space. So if you look at all of the nodes of a branch and bound tree, that says that the solution will lie in at least one of these places. And so that actually is a disjunction. Okay, now we have the disjunction. How do we get the points in the arrays? I said that using all of the points in the arrays is expensive and impractical. And so we want something compact, but ensuring validity. So here's a theorem that we use for this. Actually, the extreme rays to the PRLP define facets. So whatever points and rays that you use, the extreme ray solutions to that LP define facets of the convex hull of the points plus the conic hull of the rays. So I'll just call that the point ray hull. So a corollary is if you have a set of points and rays that somehow form a relaxation, such that point ray hull is a relaxation of your disjunctive term for each disjunctive term, then by that previous theorem, your cuts are going to be valid. This is a V-polyhedral relaxation is what we are proposing. A small set of points and rays so that we are able to capture the object, but maybe we're going to capture more than the object. So the facets might not be all the facets, and maybe they're weaker, but it's going to be compact. Maybe it's not immediately clear how you generate something like this, because if you just take a random point and you try to work with it, it's not going to give you a relaxation. So you need to choose these wisely. And so what's the idea? We're going to take each disjunctive term and we're going to optimize over it. We're going to find a solution and we're going to get the set of inequalities that are tight at that solution. Well, actually the basis, because not all the inequalities that are tight. And that actually is a cone with one point and n rays, n is the dimension of the space, for each disjunctive term. And then any cut that's valid for the union of these cones is actually valid for the disjunctive hull, because each of the cones is a relaxation of each of the terms. Okay, so we're going to call this the simple point ray collection. It's the union of those points that I just described, where each point is the optimal solution over each disjunctive term, plus the union of the rays from each of those cones. And this leads to a very reduced PRLP, point ray linear program, which just has one point for each term and n rays for each term. So it's n plus 1 times the number of disjunctive terms as the size of that LP. This is compact. And to show you that it's compact, I'm going to compare it to the lift and project LP, the CGLP, and to see how they compare, because that's the one that's used in practice most often. Okay, so the cut generating linear program, by the way, it's really nice in the sense that with a polynomial sized LP, it's able to capture every single facet of the disjunctive hull, modulo some normalization problems, which I won't talk about here. And the number of constraints is n plus 1 times t. And the number of variables is also a polynomial. And in general, for the point array linear program, the number of constraints is the cardinality of the union of the points and arrays, and the number of variables is n. And this is actually really important, because here we have an extended formulation. We have all these extra variables. And the number of those extra variables depends on the number of disjunctive terms and the number of inequalities of your original polyhedron. And it becomes very expensive to work with that as you start using stronger disjunctions. So what our contribution here with the simple PRLP is we've replaced that P union R with actually the same number of constraints as the CGLP, but we're still working with LP that is in the original dimension of the problem. Okay, so like I said, this thing is a big relaxation. We might not expect strong cuts. However, on the contrary, we have a theoretical result that says that we should. So let's suppose that we're going to work with a split disjunction first. If each of those PTs, the optimal solutions to both sides of the split disjunction, is uniquely defined, the optimal solution is unique, then actually if you use the simple PRLP, every solution you get actually defines a facet of the disjunctive hull. So that means that the cuts that you get are strong, because a facet is something that you cannot basically describe in any other way, by other inequalities that are describing the disjunctive hull. Well, anyway, that statement isn't exactly correct, but anyway. A slightly weaker version of this also holds for general disjunctions. So in other words, even though we've used this really drastic relaxation, we're able to capture strong cuts. Not all of the strong cuts, but the cuts that we do capture are strong. And so we're going to see this also play out in practice. What's the time, by the way? 15? Perfect. 20? Okay. Okay, so which objectives are we going to use? As I said, each time we solve this LP, we're going to get a cut. You might be familiar with the problem that's called cut selection in the literature, which is if you have a bunch of cuts, how do you choose the ones that are good from that selection, or that set of cuts? And this is a really hard problem that nobody has an answer to. Here, we're choosing objectives, but that's actually the same as choosing a cut. So we're going to run into this problem that we should really choose the objective selection problem here is very related to the cut selection problem. And so which objectives do we do? So the typical perspective for choosing objectives, the one that's used for the CGLP, is you take a point like x bar, and you want to cut it away by as much as possible. The issue with this perspective, in my opinion, is that as soon as you cut away x bar, it doesn't matter anymore. So if you want to generate a bunch of cuts all at the same time, and you just want a bunch of them that are cut, cannot be cut away using your disjunction. So it's a point that's in your disjunctive hull, and you're going to try to get cuts that are close to that point. And now this is a point that cannot be cut away. And so if we can find good points that we want to not cut away, then we get a lot of cuts that are close to that. That might lead us to better results. And that's actually the one that we're going to use. So this is slightly almost a nudge on cut selection too, because and it turns out that there are some people working at SCIP in Germany that have cut selection criteria that they're working on that is implemented, I think, in SCIP 6 that is very similar in the sense that what they take is they take x bar, your LP solution, and they take a solution that's actually an integer solution that's they found through heuristics or something like that, and they draw a line between those. And the way they're going to score cuts select cuts is based on where the cuts fall on that line, rather than how much they cut away X bar. So they call this the directed cutoff distance. And I think the inspiration is kind of the same perspective that we're taking here. Okay. And I might skip this in the sense that it's not that important, but the point that we look at specifically is actually of the set of points that you have from the disjunctive terms, the one that's the most important is the worst one, meaning the best one, sorry. If we're minimizing, the lowest point. And that's because that's the point that determines, so if you were using branch and bound, what is the dual bound? What is the bound that you can say? The objective value is going to be at least, or is going to be at least this value of your lowest point. Wherever the integer solution is, it's going to be somewhere above that. And since we're going to take that branch and bound tree and we're going to generate cuts and then we're going to throw it away, it would be very nice if we could capture that idea that the objective value and the optimal solution lies somewhere above this point. And so we're actually going to focus our efforts on this one point, which we're going to call P under bar, because it's the lowest point. It's actually the optimal solution not only to each disjunctive term, the disjunctive hull, but also you can find it obviously very efficiently by just optimizing over each disjunctive term individually. So that's useful. And this is important computationally, because if you work with that PRLP that we have, you might get unbounded solutions also. You also might get solutions that are the same, meaning you optimize for one objective and you get a cut. And then you optimize for a different objective and you get the same cut. Well, that means that you solved an LP, but uselessly. And an LP is very expensive to solve, so you don't want to solve too many LPs. And so what we're going to do is we're going to look at that P under bar and just focus on that one point and kind of go around the angles of it. And that's going to reduce the number of times we have to solve LPs needlessly, because if we get a cut, we know we don't have to look in that direction anymore. Okay. So I think I've made all these statements before. Some computational results. We're going to evaluate this procedure based on two metrics. The first metric is the percent gap closed, meaning for the set of instances that we're looking at, which are benchmark instances, we know the optimal value of the IP, and we know the LP solution. And what we're going to look at is how much of that gap we can close. The next thing we're going to do is we're going to look at how much these cuts affect branch and bound time. This is all implemented in an open source way. It's available actually on my GitHub page. And we use for the branch and bound tests Gurobi, but it's not necessary in general. It's just that if you test cuts, you really want to test it against something that's kind of state of the art. And if we were testing branch and bound in Coin Noir, improving that might not improve Gurobi. Okay. We limited our instances to something that are slightly smaller than the full set of benchmark instances because we wanted to run lots of experiments and our computational resources were somewhat limited. Okay. I think I've mentioned how I get the disjunctions. The way I get the partial branch and bound tree actually is strong branching. I think with a set of candidates of 5 for each node for the technical people in the audience. And the way we select each node is with minimum objective value. And we are going to test 6 different partial tree sizes, which means 6 different sizes of disjunctions. The first is just at the root node, you split into 2 variables. That's one split disjunction. That's a size 2 disjunction. Next is you stop after you have 4 leaf nodes. Then you stop after you have 8, etc., up to 2 to the 6, 64 leaf nodes. So those are the 6 disjunctions that we're going to look at. Of course, there's also the thing that we should look at, which is for each, well, anyway, okay. Let's stop there for the partial tree sizes. We're also going to set a pretty aggressive limit on the number of cuts that we're going to generate. You can generate, as I said, many, many cuts from these strong disjunctions. Since we're comparing to Gomery cuts, the number of Gomery cuts is the number of cuts you can obtain at the root node from each of the fractional variables, so that's just the number of fractional variables. That's going to be our limit. We're going to compare with the same number of cuts that you can generate using the Gomery procedure. So here's the Gomery mixed integer cuts on the average over the set of instances that I have. This is 17.3% gap closed. The V-polyhedral cuts close an additional 10% of the gap on top of the Gomery cuts. And this is reasonable because you would never just add V-polyhedral cuts. They're too expensive on their own, and Gomery cuts are so free and cheap, and I mean, they're useful, so you would always add them together. So this is probably the more relevant number. We also looked at how the cuts affect Gurobi at the root node, because that's where the cuts are done there. So this is the number, after one set of cuts by Gurobi at the root node, 26% of the gap is closed, because they add more than just Gomery cuts. They add a whole families of cuts. When you add V-polyhedral cuts, and you let Gurobi do the deciding of which ones to use, an extra 7% of the gap is closed. And after rounds of cuts, so our cuts aren't in rounds, we just do one round of cuts, the cuts that we add are still useful. They still close 6.5% more when used with the Gurobi cuts. So they continue being useful after Gurobi has done all its cut generation. Let's see. And on the instances in which we do well, we actually do quite well. So instances in which V-polyhedral cuts close at least 10% of the gap. Gomery cuts, for some reason that I don't exactly understand, actually don't do well. So somehow there's this some complementarity problem. And on their own, V-polyhedral cuts close double the amount of gap that Gomery cuts do on those instances. And anyway, we do great. That's what the numbers show. One thing I should mention, I'll mention something about this comparison later. But just remember that in the average here, something that really surprised us, even though we're generating pretty strong disjunctions, we still had an average that's lower than Gomery cuts. And yes, we know that Gomery cuts are super strong and they work well in practice, but this seems weird. And I'll talk a little bit about that later. And for branch and bound time, what we ran is an experiment in which we looked at those 6 disjunctions that we generated, plus the additional option of not generating any cuts at all. Because for some instances, cuts might not be helpful. And we're going to look at a little bit of a theoretical experiment here, in the sense that we don't really know which of these disjunctions we should use, because we're not going to add all the cuts from all the disjunctions. We're going to just add one of them. But the one that helps, for the previous results, for the gap closed, actually the 2 to the 6 disjunction is always going to be, I mean, pretty much always going to be the one that gets you the strongest cuts. For branch and bound, there are so many factors, like the density of the cuts, the way that it slows down the LP, things like that. They affect how the cuts affect the branch and bound process. So you don't know which disjunction will lead to the best cuts for branch and bound. Anyway, so what we do here is we actually report the best time across all of those 7 options that I described. And this is Gurobi reported with 7 random seeds, and the best of that. Okay, so that is, oh actually no, so this is not the Gurobi with the best of 7 random seeds. I have those numbers, but here it's actually just the Gurobi by itself. And this is what would happen in the very theoretical experiment in which we know which of those disjunctions to use, or whether or not to use any of the cuts. This is the improvement that you would see if we could solve what seems like not that hard of a machine learning problem. Given 7 options, how do you choose among them, given a whole bunch of data? So this is kind of the my postdoc pitch when I was going to work for my postdoc is that I think that there is a feasible machine learning problem to go improve from 81 seconds of shifted geometric mean time to 63 seconds by solving the problem of when do I generate cuts, and if I generate cuts, which of these 6 options should I use? Just knowing that will get you that improvement. And so this is the results not counting cut generation, and this is counting cut generation. And cut generation, as you can see, doesn't really affect things all that much. It's relatively cheap on average.
Sorry, that's the average time of the...
Shifted geometric mean, shifted by 60 seconds.
But it's for all the instances?
For all of the instances, yes, for all the instances. I think there are some missing that are, I think the ones that you could find the solution within 64 nodes, I just discarded those. So 2 easy instances. Okay, how much time do I have? 5 minutes? Okay, so I'll take 10. So I mentioned this number, the 15% and the 17. And we thought about it, and Egon had, my advisor had an observation. Gomery mixed integer cuts use a strengthening procedure in there. So there's a cut that you get from a split, but actually Gomery cuts, if you look at the formula, they end up using a tilted split, because if you look at the geometry at least. But they use something called monoidal strengthening or other methods that you might use to derive it. Our cuts do not have any strengthening applied to them. It's a post hoc strengthening. You've gotten the cut, but now you look at integer variables that are non-basic at the root, and you use a formula from that just to apply it on the Gomery cut, and you get the Gomery mixed integer cut. And we know that in practice, this is really, really important. And for our cuts, we can't do it. We can't do it because we need some information that we don't have. That's what I'm going to try to tackle here. So just to review a little bit, here's what a disjunction looks like. This cross disjunction that I had before, but now I'm going to actually display the disjunctive terms. So these are the disjunctive terms. And here was x bar. And now here's a cut, alpha transpose x greater than or equal to beta. It's in this direction. And over there on the right is, for each PT, it's the Farkas certificate for alpha beta. And what does that mean geometrically? It actually means that the normal to the cut lies in the cone defined by AT and BT for each of those terms. Because it's a conic combination of inequalities. And it turns out that the problem that we really need to solve is, can we compute those VTs, but we don't want to solve the CGLP, the higher dimensional linear program that's used for lift and project cuts. And that's crucial for strengthening. Because, don't look at the formulas too much, but over here, this is a strengthened coefficient, and this is the original coefficient. And the way you obtain the strengthened coefficient is you use UK and U0 here as I broke up V in some components, but these are essentially the V's. And you need to use the values of those V's. If you have the values of those V's, then you can apply the strengthening approach that's in the literature. Okay. And our theorem informally is basically we can do it. That's what that says. So here's for some intuition, let's start with the simple case. Let's say that AT is invertible. So if AT is invertible, we have from the Farkas certificate, we know that alpha bar is equal to V bar transpose for some V bar times AT. Well, then the value of V bar T, this is a T is like the disjunctive term T, can be calculated by just taking the inverse. So that's just a computation of an inverse. It's very cheap, relatively speaking. You don't have to solve an LP. And when does this apply? Actually, in the simple PRLP case, it already applies. Because each of our relaxations is a cone. Each of those cones actually leads to invertible AT. Because, well, anyway, it does. And I think that that's a very positive thing for us, because that means that, in principle, we don't have to do very much to generate some strengthening. We have to solve the inverse problem, which we should already have, actually, available for us from the code, and then test that strengthening in practice, which we haven't done yet. However, that theorem goes more general, because also the V-polyhedral cut framework is more general. We don't want to limit ourselves to these, something that's a closer representation of your disjunctive term. The general case, it turns out, is reducible to the simple case. And that's also a theorem. And the idea is basically you take a basis on each disjunctive term. And once you have a basis is invertible, which is why those cones that we use for the simple PRLP are invertible. And you can reduce it to the simple case. Okay, and so this enables our ongoing strengthening research. So in conclusion, we present a framework, a pretty general framework for generating disjunctive cuts. And we utilize structural properties in there, in our algorithms, in order to try to get good objectives, good cuts, more efficient approaches. We're missing this coefficient modularization, the strengthening that I mentioned. But we are able to use our previous theorem to try to work on it and test whether we can do the cut strengthening. So other things that I'm thinking about, I think that V-polyhedral cuts make a nice connection between branching and cutting. They almost seem like different things, right? But in my perspective and from this cut generation framework, you can see that they're kind of tightly linked. Because you go branch, you actually generate disjunctions. Disjunctions lead to cuts. Cuts can be used to re-optimize. Which disjunction should you use for cuts, for example? That's an interesting question. Maybe the way that we are generating our partial branch and bound trees here are the same ways that you would generate a branch and bound tree if you were searching for the integer optimal solution. But maybe those are not the places that you should look for cuts, because maybe cuts in a different space, in a different part of the space might help you more, because the branch and bound tree later will look at those things anyway. It's all philosophizing, but understanding how cuts affect branching and how branching affect cuts, this is still a very poorly and difficult to understand area. And as I said, we maybe can start looking at cut selection issues with this, because we can generate a lot of cuts. And figuring out which ones are helpful, maybe we can get enough data here. And lastly, we can also extend things to nonlinear settings with not too much work. I haven't done the experiments on that yet, but I am interested in that in the future. Okay, thank you for your attention. Any questions?
Thanks a lot, Alex. Any last questions? Any last questions?
Well, thank you for the invitation again.
Well, thank you.
And thank you for the attention again.
Good.
45 minutes, 50?